Welcome to another anatomy video. In this video, I'm going to be going over the typical features and structures of a standard long bone, as well as pulling out that compact bone model that I'm sure you're all too familiar with from your labs. Because of the size of this video and the length that it's going to take to explain all this information, I'm not going to have the part where you can test yourself at the end of this video. It's actually going to be in another video. The link of which is going to be right below in the description. So if you feel like you already know this material and you just want to test yourself, go ahead and you can just skip this, click the link down there, and you can just go ahead and test yourself on that video. However, if you feel like you don't know this material well enough and you want a little lesson on it, well, that's what I'm going to be doing right now. So without much further ado, let's just go ahead and jump right on in. Okay, so this is going to be the first image that we're going to be viewing in this lesson. This is a picture of a long bone. The body's bones can be classified one of 6 different ways. A bone can either be classified as a long bone, a short bone, an irregular bone, a flat bone, a sesamoid bone, or a sutural bone. And in this image, we're going to be looking at the typical makeup of a long bone. They comprise many different bones in the body, and this is the standard model. So the first thing that we'll be breaking down are the 3 different regions. The very first region is this middle region known as the diaphysis. It's also sometimes referred to as the shaft of the bone. And so you're going to have the diaphysis right here. On either side, just outside of the diaphysis, are the regions known as the metaphysis. And then we have the epiphysis on the very outside just past that. The terms proximal versus distal refer to the fact that this epiphysis, is closer to the site of attachment to the body, and that's what the term proximal refers to, whereas distal refers to being further away from the site of attachment. So the distal end would be down here, the proximal end would be up here, and that's where we get the terms proximal versus distal. I know when I was taking the course, I struggled remembering these regions in order, so I could always remember diaphysis, but metaphysis and epiphysis I always just seem to mix up. And so I came up with a little mnemonic, and hopefully it helps you out. If it doesn't, you can always make up your own as well. But I just remember the mnemonic, don't make errors. So don't, right, for diaphysis, the D for diaphysis, the D for don't, and then make for metaphysis, and then errors for epiphysis. So if you can remember that, that can be kind of helpful. Don't make errors. Don't make errors. So hopefully that can help you. Inside of both the metaphysis and the epiphysis is a type of bone known as spongy bone. And spongy bone gets its name from the spongy texture that we see here. It's a very porous type of bone. And inside that negative space of the spongy bone, we find a substance known as red bone marrow. Red bone marrow is actually the site of hemopoiesis, which is the production of the blood cells in the body. So we have hemopoiesis occurring in both the metaphysis as well as the epiphysis. In between these 2 regions is this line right here, and this is actually known as the epiphyseal line. If this was in a growing child, it would actually not be an area of bone, it would be an area of hyaline cartilage that allows for longitudinal growth in the bone as we're developing, especially like during puberty and things like that. And so it was called the epiphyseal plate because it's an area of hyaline cartilage. However, at about the age of 25 or so, this fully ossifies and the cartilage turns to bone. So we see this epiphyseal line now. So again, it goes from epiphyseal plate when we're young to epiphyseal line when we're older. And in a x-ray, this would actually show up on the x-ray as its own line. On a child, actually, because it's an area of hyaline cartilage, if you were to take an x-ray of a child's humerus, you would, or really any long bone for that matter, it would almost look like there's a fracture here because the hyaline cartilage would not be picked up by the x-ray. And so it would almost look like the metaphysis and the epiphysis were separated. The important thing about this line is that it's kind of the separating line between the metaphysis region and the epiphysis. So that's one of the important things about this epiphyseal line. Going around the bone itself, we see an area of connective tissue. They've kind of got it cut away right here. And this is known as the periosteum. Peri is referring to surround or wrap around something. So an osteum is just referring to the bone, so that's where we get the term periosteum. On the inside, lining an area known as the medullary cavity, which I'll talk about in just a second, we also find a membrane known as the endosteum, endo referring to on the inside. So the membrane on the inside of the bone in the medullary cavity is known as the endosteum. We see that in blue here. This region is known as the medullary cavity. It's a hollowed out space inside of the bones, and what it actually does is it allows for our bones to be a lot lighter, which is a very, very good thing. It allows for us to be able to move much quicker, as well as use fewer calories when we're trying to move our bodies. I know in today's day and age, we're all about trying to burn as many calories as possible because of the copious amounts of calories that we sometimes consume with our diets. But if you look back to the days of like the hunter-gatherers and things like that, this is a very important thing to have because calories are much more scarce, so we wanted to use as few of them as possible. And having a hollowed out bones was a very nice way to expend less calories to move from place to place. The medullary cavity is also going to be filled with a substance known as yellow bone marrow, and yellow bone marrow is filled with adipose tissue, so it's fat storage. So it's used for energy reserves and things like that. So again, in the medullary cavity, we have yellow bone marrow, which you can't see on this image, whereas in the epiphysis and metaphysis, we find red bone marrow, which again was that site of hemopoiesis. So two different distinctions there, and make sure that you can tell the difference between the two. On the outside of the bones, we also find hyaline cartilage. At the head of the humerus, we find it right here, and we also find it down here at the distal epiphysis as well, going over an area right here known as the trochlea, as well as the capitulum. And then again over the head of the humerus, because the head of the humerus is going to articulate with the glenoid cavity of the scapula. And wherever we have those articulations, we definitely would want hyaline cartilage, because without it, we would have bone on bone, and that would be very painful. So it kind of reduces friction. They're also used for shock absorption as well. So again, this is an area of hyaline cartilage, and you have hyaline cartilage down here as well. All right, the next thing that I'm going to be going into is compact bone. And compact bone is actually found on the outsides here, and it runs primarily through the diaphysis, is where we're going to be taking our model from. The model that I'm going to show you, and I'll show it a little bit better on the next image, but I've noticed that a lot of students have trouble even really understanding what it is that they're looking at. And what the model is actually doing is, imagine if I were to take this area right here and I would just cut a pizza wedge slice out of it. Okay, that's going to be what the model is trying to represent. And I'll go ahead and just jump right into that model right now. Okay, so this is probably the model that you're already familiar with seeing in the lab, and again, what we're looking at here is that slice of the compact bone taken out of the diaphysis. So what I want you to imagine one more time is that if I took this bone and I sliced it in half, and then I looked down on it from a superior view, so I was looking down at that slice that I just made, we would have the medullary cavity right here, as well as the area of compact bone surrounding it. And unfortunately on this image, I didn't have enough room, so it's going to get cut off, but this would make an entire circle going around the medullary cavity. And this whole area would be compact bone. So here is another view of that model. I'm going to be using this image primarily to be going over the main structures of and features of the compact bone. First, we'll be starting off in here. We'll talk about this blue membrane. This is going to be that membrane that lines the medullary cavity, and so this is going to be known as the endosteum. Whereas on the outside over here, wrapping around the outside of the bone, this would be, again, the periosteum. The periosteum is held to the compact bone via these fibers right here, known as perforating fibers, also referred to as Sharpie's fibers. And that's what those are going to be right here, and they connect and hold the periosteum to the compact bone. The next structure that we're going to talk about are the osteons, and what an osteon is an individual column of bone tissue. And so we see that right here. It's actually been divided into its separate layers, which I'll talk about in just a minute. But this whole structure is an osteon. You'd also see an osteon right here as well. So this whole column right here. The only difference between these two is that this model has just decided to elevate this one to show you the osteon a little bit better. And so actually we'd see an osteon over here as well. Osteons are made up of individual rings known as lamella. So this right here would be a lamella. This would be a lamella. You have a lamella here, lamella right here. On this osteon, you'd see the lamella right here, right here, right here, so on and so forth. And a nice analogy that I like to use is viewing the osteon as an entire tree trunk and the individual lamella as kind of the concentric rings essentially that make up the tree trunk itself. There's also a feature on here known as an interstitial lamella, and what an interstitial lamella is it's essentially an osteon that's been overrun by newer incoming osteons, so we only see parts of its lamella anymore. So this right here, I highlighted it in pencil on this model so you can see a little bit better, would be an example of an interstitial lamella, and you would also find one right here. The reason that these exist is because the bone is constantly reforming and remodeling itself, and as such, the newer osteons are overrunning older osteons. So again, when we look at this image, I almost like to think of it as dropping pebbles into a nice glass pond, if you will. And when you drop the pebbles on, the last one that was dropped would obviously be this one right here, because it's clearly overrunning the ripples from a pebble that would have been dropped earlier. So this would be the newer osteon, this would be an older osteon. That analogy might help you just kind of see this model a little bit differently. But yeah, that's where we get interstitial lamella from. The next three structures that I'm going to be talking about are the three different types of channels that we find in the compact bone. The reason that we find these channels is because, again, this bone is living tissue and it has living cells in it, and in order for those to survive, they need to receive nutrients, have waste taken away, just like any other cell in the body. And so in order to do that, we have these channels that the blood vessels are going to run through to supply the cells with what they need. So the first channel that we're going to see is something called the perforating canal, and we see it right here. Again, it has that periosteal artery running through it, but you can imagine that if you took this vessel away, that it would be running through a canal. So much like you had the perforating fibers attaching the periosteum to the compact bone, you also find a perforating canal running into the bone. The perforating canal then meets up with a canal known as the central canal or Haversian canal, and those run through the very center of the entire osteon. So you'd have a central canal running right here, right here. This would be a central canal, right? The final canal that the nutrients from the blood are going to be running through in order to supply these living cells, these osteocytes, with nutrients are going to be the canaliculi. I'm actually going to jump over here because I highlighted them in pencil so you can see them a little bit better. But they're just these small indentations that we see that radiate in between each of the lamella. And so here's the analogy that I want you to use when you're trying to maybe recall these for the exam. Imagine driving home, and the main road that you go on is the freeway. And so the freeway would be, in this analogy, likened to the perforating canal. Once you get off the freeway, you get onto your main highway, which would be the central canal. And then in order to get to your house, you have to turn off the highway and get onto your side streets. And the side streets would essentially then be these canaliculi. And the canaliculi take you to your home. In this analogy, here's a new term for you, it would be the lacuna. And what a lacuna is it's essentially these little pits that the osteocytes lay in. So you can think of them as the osteocyte's house. So that also fits into this analogy. So osteocytes lay in this lacuna, and in order to get their nutrients, the blood has to travel through the perforating canal, up the central canal, also referred to as the Haversian canal, and then through the canaliculi to get to the lacuna where the osteocytes are laying. Before I move on to what I believe to be our final term that we're going to really be looking at in this video, I want to let you know that just because we don't see osteocytes in this model inside of these lacuna, they do exist in here. The model just shows the osteocytes over here, but again, these osteocytes are laying in their own lacuna, but they would be also living in these as well. The model has just decided to show you different regions differently, just so you can kind of get a feel for what's happening. But just be familiar with that these have osteocytes in them too, and these osteocytes over here are also laying in lacuna. So the final term that I'll be discussing in this video are structures known as trabeculae, and what trabeculae are the projections of compact bone that make up the spongy bone. So this right here was, again, the wall of the medullary cavity. We see that blue membrane, that endosteum lining the medullary cavity, and there's a thin layer of spongy bone on the wall of the medullary cavity, and the projections of compact bone that make up that spongy bone are what we call the trabeculae. So this would be an example of a trabeculae, this would be an example of a trabeculae, this would be an example of a trabeculae. If we look at another rendering of it, we actually see that if we were to slice this area of bone that makes up the spongy bone, it looks a lot like that compact bone model that we were talking about before. And so that's what I'm talking about when I'm saying that the trabeculae are projections of compact bone that make up the spongy bone. So again, this would be a trabeculae, and this would be a trabeculae as well. So there you have it. So the next thing that you can do is, if you feel like you understand this material well enough, you can go ahead and click on the link on the description below and feel free to use that video to test yourself. Again, the way that it works is I'll be throwing up images on that video, giving you a second or two in between them to pause, answer whatever question it was that I gave you, and then hit play again, and the answer will pop right on up. Again, obviously, if you feel like you don't understand the material well enough still and you want to review this again, obviously you're more than welcome to as many times as you want. So best of luck to you on the exam, and hopefully I'll see you soon in another anatomy video.